Hey guys, 7.6 factoring polynomials. Screencast for cubic functions. This is the intro. So this is before we've done anything with this. So you should have your handout. So it says, imagine a cube of any size. How do you find the volume of a cube? So if you're as good of an artist as I am, we can draw a cube. So there's a cube, and we find volume of any 3D figure by finding the area of one of those faces. So a face is a square, so you have length times width, and then you multiply it by the height, now that we have a third dimension. So since this is a cube, it has that special property that all sides are the same. So your height would be x, your length would be x, and your width would be x. So this could be written, volume equals x times x times x, or volume equals x cubed. Now, why do we say x cubed? Well, because it's finding a volume of a cube. So this is called a cubic function. So we know quadratic functions have the highest power of x is squared. That's how you know it's quadratic. Cubic functions, the highest power of x is a 3, so that it is cubed. Okay, so next part says, imagine increasing the height by 2, the width by 3, and the length by 4. What would that cube look like now, and what would the volume be? So here's where we get into some actual cubic functions. So now we're increasing height, width, and length, and since we're increasing them by different numbers, we no longer have a cube, but we moreover have a rectangular prism. So that might look something like this, and again, you can try to copy my amazing drawing skills. The front's going to be a little bit bigger than the back, but we'll make do. Ta-da! Didn't know I was so talented, did ya? All right, so it said increase the height by 2. So my height, which, give me a different color, which is over here, is going to be increased by 2. So this was originally x. Now I'm adding, I'm adding 2. And the width by 3, so my width was x. Now I'm adding 3 to that. And the length by 4. Again, the length was x, and now I'm adding 4 to that. So what would my volume be now? Well, volume is still length times width times height, but now my length, width, and height are not just x's, they're these parentheses. So volume would be x plus 4 times x plus 3 times x plus 2. And we've done problems like this. In fact, it was on the last test where we have to FOIL and simplify and then FOIL again. And we come up with another cubic function. So I'm not going to have enough room to do that here, but I left you plenty of room on your paper. So let me go on to the next slide here. Rewrite that equation. X plus 4 plus x plus 3 plus x plus 2. Whoops. And let's multiply it out. Again, you could use an area model if you like. So if you want, draw your area model. You would have x and 4, x and 3. Multiply it out. You should end up with x squared plus 3x plus 4x plus 12. Now that's only the first two sets of parentheses. You can't do all three at once. It's only the first two sets of parentheses. I'm going to keep that x plus 2 there. I'm going to continue to simplify because I can combine these two terms. So I have x squared plus 7x plus 12, and I still have x plus 2 on the end. Okay, so now I have to multiply all of that out. So again, I could use an area model. This time I would have 3 by 2. So I'd have x squared, 7x, and 12, and then x and 2 here, and I would fill in all of these pieces, and you should get x to the third plus 2x squared plus 7x squared plus 14x plus 12x plus 24. Maybe not necessarily in that order in your square or in your rectangle, the area model, but all of those numbers nonetheless. So now again, combine like terms. So I have x to the third, no other x to the third, so that stays. 2x squared, 7x squared is 9x squared. 14x and 12x makes 26x. Plus the last one on the end, 24. So again, this is a cubic function, and it represents that situation of increasing that cube by a certain number each time. Okay, so that would be the volume of that cube, and then if we knew what x was, obviously we could plug that in and find the actual volume. A third degree polynomial is called a cubic function. Let's write that down. A third degree, remember degree are just your exponents. A third degree polynomial is called a cubic function. Okay. And it shows you down there at the bottom what the graph looks like. So let me insert that here just so I could talk about it for a minute. So here is what the graph looks like. So what you see here is instead of a quadratic equation where we would have something like a parabola, like so, I'm sorry this is so dark, we would have two x-intercepts. We now have a cubic function. It's a third degree polynomial, and most of them have 3 x-intercepts. In fact, those 3 x-intercepts correspond directly to that equation, that first equation in factored form. What was the equation in factored form? X plus 4, x plus 3, and x plus 2. So guess what your x-intercepts are? This x-intercept, x equals negative 4. This x-intercept, x equals negative 3. And this x-intercept, x equals negative 2. So zero product property works just like it does for a quadratic. It works the same way for a cubic function. Once you're in factored form, which is what we have here, right? Factored form, and zero product property, you know I do ZPP, will work, right? Either x plus 4 is 0, which is how you would get negative 4, or x plus 3 is 0, which is how you find out x is negative 3, or x plus 2 is 0, which is how you get x equals negative 2 once you solve those, and those correspond to your x-intercepts. So that is the same for a cubic function, just like it is for a quadratic function. Okay, so let's practice writing cubic functions from graphs. It's a lot easier than you might think. So I have 4 steps that you're going to fill in on your page. So step 1 here is to locate x-intercepts, just like we did on that last graph. Okay, these are your roots of the function. Remember, the roots, they're also called zeros, and they're also called solutions. They have many names. When we talk about writing in an equation, we talk about the roots, though. Second step is to put the x-intercepts into factored form. So put x-intercepts, which again are your roots, into factored form. Factored form is pretty much the same as it was for quadratics, but cubics have a third one, so now you have 3 roots. So factored form is y equals a times x minus r1 times x minus r2, and now we have x minus r3 because we have 3 roots because of, like I was showing you, the graph now touches the x-axis at 3 different points. The third step is to find A, and I'll show you how to do that. I'll show you the long way and then I'll show you the shortcut depending on what you have, what information you have. So find A. So remember, that's your scale factor. That's your vertical scale factor. And you find it by plugging in a different coordinate and solving for A. Again, I'll show you how this works. Okay, and then your last step 4 is to rewrite the equation with the A value. Rewrite the equation with the A value. Sorry, but no matter what I do, I can't get my writing to look any better on this thing. So hopefully you can read that. Pause it if you need to get the rest of the steps down, because I'm going to go on to examples now. So you have there example A, write cubic functions for the graphs below. So I'm going to take that first graph. This is going to take up the whole screen, and for some reason I can't find out how to make this any tinier. I can only move it around the screen, so hopefully I'll have enough room to do this here. Okay, I'm not going to have enough room, so I'm going to be flipping back and forth. Sorry. The nice thing about this graph is they've given us our x coordinates, so our x-intercepts rather. Had they not given us those exact numbers, this would be a lot more difficult because we would need to locate them, and since they're in between integers, that would have been a little bit more difficult. But they were nice enough to give us our x-intercepts. So here's one x-intercept at negative 2.5. So there's one, x equals negative 2.5. Here's another, and x equals 3.2. And the third, so x equals 7.5. So those are our 3 x-intercepts. That's step 1, easy enough. So I'm just going to put step 1, x equals, I don't even remember them, 7.5, x equals 3.2, and x equals negative 2.5. Okay, so step 2 is to put them in that equation. So if x equals 7.5, that's root 1, root 2, and root 3. And it doesn't matter which ones are which. I could have made this root 3 and this root 1. It really does not matter. As long as you have all 3 of them, I just went in order. 1, 2, 3. So the equation would be y equals, I don't know my a value, so I'm going to leave it as a for now, times, whoops, I don't know how that happened either. What is going on here? Get bigger again. How did that happen? Oh, yeah. Okay, whatever. Continuing on. So x minus root 1 is 7.5 times x minus 3.2, that's root 2, times x minus negative 2.5, because that's root 3. Now, if you're asking yourself, why am I writing minus? Go back and look at the equation. The equation was all subtraction. Here it is. Okay? So the equation has all subtraction, so when I write the equation, I have to use it correctly and put the subtraction. Now, the first two are pretty good. This last one, though, you know, we're changing that from minus the negative to addition. So the equation right now is a times x minus 7.5, x minus 3.2, x plus 2.5. So now here's that step where we have to find a. So step 3, we're finding a. And it says to find another coordinate pair, and then we're going to plug it in. So I'm going to go back to the graph. They're giving us another coordinate pair right here. So I'm going to use that. So my x value is 0, My y value is 240. So I'm going to plug that into the equation I just wrote in step 2. X is going to be 0, y is going to be 240. So let me go back here. So x is going to be 0. So everywhere I see an x, I'm going to put zeros for step 3. And y is 240 because of the point I'm using is 0, 240. So x and y. So my equation then is going to read, not y equals, silly, 240 equals a times 0 minus 7.5 times 0 minus 3.2 times 0 plus 2.5. Now obviously you don't have to write all of that once you get the hang of it, because 0 minus 7.5 is just negative 7.5, 0 minus 3.2 is negative 3.2, and 0 plus 2.5 is just 2.5. So the numbers themselves just kind of come out of that equation. So we multiply all these guys together. So I have 240 equals a times, this becomes 60, and we solve. How do I solve for a? Well, if I have something multiplying a, then I divide it out, and 240 divided by 60 is 4. So a is equal to 4. So step 4, of course I ran out of room, step 4 is just to put a into that equation. So now I have y equals 4 instead of a, and then my parentheses, x minus 7.5 times x minus 3.2 times x plus 2.5. And there is my final answer for that first example. Okay? So the more annoying part is that finding a. And unfortunately there's no shortcut to this one because we have a graph. So there's no way I can just determine a any other way besides plugging in a number. Okay? So let's look at example 2. If you want to try that yourself and then check your work, that would be cool too. All right. So here's example 2. Remember, first step, x-intercepts. So that's not example 2. Did I do oh, it is example 2. Oh, it just looks a little bit different because now we've changed our scale factor, but our x-intercepts are the same. Well, that's nice. X-intercept, x-intercept, x-intercept. So negative 2.5, 3.2, 7.5. So step 1, x equals negative 2.5, x equals 3.2, and x equals 7.5. And those are my roots. So root 1, root 2, root 3. So when I do the equation in step 2, the equation... Alright, so somehow I paused recording, and I don't want to restart everything, so I don't know where I left off. But here's example 2. If I'm repeating myself, I'm sorry. Here's example 2. So far what we've done is we've identified our x-intercepts, which were in yellow. Okay? Identified the x-intercepts, which are the same in example 1, and I've written them out for step 1. Here we go. Okay? Then I put them into the equation for step 2. So root 1, root 2, root 3. The first root was negative, so it changed to the positive right there. And now I'm on for step 3, looking for the other point that we're going to use in the equation. So hopefully I didn't leave anything out, but I know that when you come to class next, you'll let me know if I did. So back at the equation, or back at the graph rather, we found another point. They've labeled it 0, negative 90, so x is 0, y is negative 90. So that's what I'm going to use when I plug into the equation that we wrote in step 2. So here's x, here's y. So I'm going to plug in negative 90 equals a, that's what I'm trying to find, times, and then I plug in my zeros. So 0 plus 2.5, yes, you can skip this step, 0 minus 3.2, and 0 minus 7.5. Okay, so negative 90 equals a times 2.5 times negative 3.2 and times negative 7.5. And when we multiply those together, we get a times 60. So we divide here to solve for a, divide by 60, divide by 60. So you find out a equals negative 1.5. So now for step 4, I'm going to squeeze it in here. So step 4, we take the equation from step 2 and just put in a. So we get y equals negative 1.5 times x plus 2.5 times x minus 3.2 times x minus 7.5. And I went off the screen. See what happens when you try to squeeze things in. Let's make that prettier. Negative 1.5 times x plus 2.5, x minus 3.2, and x minus 7.5. There we go. That fits. So this would be the final answer for that quadratic function. Okay, so I'm sorry for the little cutout in the middle. I have no idea how I accidentally paused it, but I didn't want to have to go back and redo all of that work already. So hopefully I didn't miss anything important. If I did, let me know when you come to class and we will work it out. All right? See you soon.